This is where we left off on Monday. We were talking about the Celsius and the Fahrenheit scales. Actually, let's go back to this picture showing the relative temperatures. We use water boiling as a reference, 212 on the Fahrenheit, 100 on the Celsius, 373 on the Kelvin scale. To convert between these temperature scales, we generally need to use an equation. So these are the equations down here. If you have the Fahrenheit temperature and you want the Celsius temperature, you would use this equation. You take the Fahrenheit, you subtract 32, and divide by 1.8. If you have the Celsius and want the Fahrenheit, then you need to rearrange the equation. Kelvin to Celsius is a simpler equation because it's just offset in at zero. The size of the divisions are the same. So I do want to show you something extra. So we'll go to the whiteboard here. So on the Fahrenheit scale, we've got 212 for boiling and 32 for freezing. And in between, that's 180 divisions. So this is the Fahrenheit. On the Celsius scale, the same difference in temperature goes from 0 to 100. So that's 100 divisions, and that's Celsius. So you can memorize the equation. I'm not going to give you that equation. Or you can also reason it out. If I have some number of degrees Fahrenheit and I want to find out what the Celsius temperature is, first I need to subtract 32 because the Fahrenheit scale is 32 degrees above the Celsius scale. And then I'm going to multiply that by 100 degrees Celsius for every 180 degrees Fahrenheit. And actually this should be degrees Fahrenheit. So we take the Fahrenheit temperature, we subtract 32, and then we use this 100 Celsius per 180 Fahrenheit to convert. And that will give you the same equation. Some of you are real good at memorizing equations. Other people prefer to understand why. Then on a test, you can just reason it out. If you're going the other way and you have degrees Celsius, you're going to convert to Fahrenheit by multiplying by 180 degrees Fahrenheit per 100 degrees Celsius. Those Celsius units will cancel out, and then you'll you'll add the 32 degrees Fahrenheit to get the Fahrenheit scale. We're going to get some practice with this when we do the worksheet. If figuring out these equations didn't make any sense to you, just go with memorizing the ones that are given. Let's do an example. Gallium is a really cool element. It's a solid at room temperature, but it will actually melt in your hand. So the melting point is 85.6 degrees Fahrenheit, and the question is asking, what is this temperature on the Celsius scale? And then the second part is, what is the temperature on the Kelvin scale? So we're given a temperature in degrees Fahrenheit, and we're asked to convert to Celsius. So for A, we're going from 85.6 degrees Fahrenheit, we're converting to degrees Celsius. This is a conversion between units that requires an equation. So you would look the equation up or figure it out like I just showed you. The Celsius temperature equals the Fahrenheit temperature minus 32 divided by 1.8. That's the equation given in the book. Then we're going to take our Fahrenheit temperature, 85.6 minus 32, divide by 1.8. When I do calculations like this during lecture, I would really like you to have your calculator out and punch the numbers in too. because I make mistakes. And it's really fun to say, hey teacher, you got it wrong, right? I'd like to say I do that occasionally just to see if you're on your toes, but I just plain old make mistakes. So my calculator is showing me 29.77777, a whole bunch of sevens. Anybody else get that? Yeah. Okay. When you do a calculation on your calculator and you care if the answer is right or not, do it twice. Very easy to miss a button, punch a button twice. If you do it twice and get the same answer, you probably communicated with your calculator correctly. If you get two different answers, go for best 2 out of 3. So I'm doing it, and then I'm relying on you guys to be the duplicate. We're going to talk about significant figures later today, but for now, this is an awful lot of digits, isn't it? What we should do with temperatures is look and see how many decimal places the original temperature had. This one has 1 decimal place, and so then we should report this with 1 decimal place. And so we'll say that the answer is 29.8 degrees Celsius. Any questions? Most of the stuff we're covering in this chapter should be review for you. So what's this temperature on the Kelvin scale? Do we want to use the Fahrenheit temperature or the Celsius temperature to convert to Kelvin? We're going to use Celsius because the equation that we're given starts with Celsius. So again, we're going to just plug our number in. Here we've got the 29.8, and we're adding to 73.15. Calculator says 302.95. The unit is Kelvin, not degrees Kelvin, but just plain Kelvin. And again, what I said earlier, look at the original temperature. It had 1 decimal place. Let's round this to 1 decimal place. What would that be? 303.0. And this, we'll talk more about this rounding, but the number that we're dropping is 5 or greater, so that rounds the 9 up to a 10. That bumps the 2 up to a 3. Any questions? We mentioned the metric system. The metric system, I think, is awesome. It really helps to have an understanding of scientific notation. I'm not going to go over scientific notation in lecture. You should know that from your prereq class. If you need a review of that, you can consult Appendix 1A in your textbook, and feel free to ask me outside of class, but I'm going to assume that you're okay with scientific notation. The metric system uses prefixes that multiply the units, making them larger or smaller. And these are all by powers of 10. Just like the exponent in scientific notation multiplies the number. So the example here is kilometer. The prefix on the unit is kilo. Kilo means 1,000 or 10 to the 3rd power. So 1 kilometer is equal to 1,000 meters. It makes the meter larger. So it's 1,000 meters instead of a regular meter. Or we can express it this way. So let's do another one. The prefix centi means 10 to the minus 2. So if we take 1 gram, 1 centigram is equal to, instead of centi, we're going to put what centi means, 10 to the minus 2. So 1 centigram is 10 to the minus 2 grams. It is very important to get a handle on the metric system. Okay, and we'll get some practice on the worksheet as well. If you have trouble with that, please ask for help today. This is one of my favorite things to explain, and I can explain it about 15 different ways, so I'm pretty sure I can get through. These are the metric prefixes. I'm not making you memorize all of them, but as you see, they're all powers of 10. And I think it's a lot more helpful to just remember the 10 to the something instead of trying to do it like this. Because once you get past about 3 zeros, you have to get your finger out and count. And that just makes me feel like a child. I don't like to do that. And it's a shame to get a problem wrong because you counted zeros incorrectly. Most of these, the exponent is a factor of 3. So they go up by 3s. 10 to the third, 10 to the 6th, 10 to the 9, 10 to the 12. The exceptions are the ones right here in the middle, 10 to the minus 1, 10 to the minus 2. There are some other ones that are not listed on here, but in the memorization quiz material are the ones that I want you to know for this class. So let's use these prefixes. How long is 4.5 megameters in meters? Well, what does mega mean? 10 to the what?
6.
It means 10 to the 6. So we can look up in the table, if we haven't memorized it yet, that mega equals 10 to the 6th. So if I take 4.5 megameters, instead of mega, I can write what it means. That's 4.5 times 10 to the 6th meters. You see how that works? If we have a volume of 7.13 times 10 to the minus 9 liters, what would the equivalent be in nanoliters? What does nano mean? 10 to the minus 9. I find that one easy to remember because nano and 9 are similar. Nano means 10 to the minus 9. So instead of this 10 to the minus 9, I can write the prefix nano. So this would be 7.13 nanoliters. Any questions? We've been talking about basic units. There are also derived units that are combinations of other units. The one we use most frequently in chemistry is volume. But other examples are speed or rate, such as miles per hour or meters per second. It involves a unit of length and a unit of time. Volume measures space. If you take a unit of length and cube it, it becomes a volume unit. So if we, well, first we need to select our drawing tool. So if we have a cube, we have a, well, this would be the height and the width and the length. From geometry, hopefully you remember that the volume is equal to the length times the width times the height. Each of these sides is measured with a unit of length, right? Because it is a length. When we multiply those together, then we get a unit of volume. Typical units we use in chemistry are liters and milliliters, and those are related to cubic centimeters. So here's an illustration, a cube that is 10 centimeters on a side. So then what's the volume of that? Well, one side is 10 centimeters, and another side is 10 centimeters, and another side is 10 centimeters. So that's going to equal 1,000 centimeters cubed. And if you look at these individual little cubes inside the big cube, these little guys, if you count them up, there's 1,000 of them. Each of these little ones is 1 cubic centimeter, and together 1,000 of them make up 1,000 cubic centimeters. One cubic centimeter has a special name. We call that a milliliter. What does the prefix milli mean? Does anybody remember? 10 to the negative 3. So 1 milliliter is 1 times 10 to the minus 3 liters. This big cube here has how many of these small ones in it? 1,000. So the volume of this large cube is 1,000 cubic centimeters, which is equal to 1,000 milliliters, which would be 1,000 times 10 to the minus 3 liters. And 1,000 times 10 to the minus 3 is 1. 1 liter. 1 liter is 1,000 milliliters. Here are some common units and their equivalents. There's relations. Most of these are English system to metric. This table is in your textbook, and you may need to refer to it when you're doing some problems. A kilometer is 0.6214 miles. 1 foot is this many centimeters. 1 inch is this many centimeters. These relate mass, and these relate volume.
During a test, will we give them that, or would we know it already?
That's a good question. During a test, would you be given these, or would you need to know them? I will tell you the ones that I think you need to memorize. I think you need to memorize this guy right here. 1 cubic centimeter equals 1 milliliter. That's a very easy relationship that students tend to forget about. And then that makes a problem really hard when you're missing that little piece. The other one that I think is really important is inches to centimeters. That's one that you should memorize. The rest of them, if you need them in an exam question, I will give you the relationships. I don't expect you to remember how many quarts are in a liter. I don't remember that myself. I look it up. You do need to know metric prefixes, and you should be able to do any metric conversions. The awesome thing about those metric prefixes is they are used for all of the units. So you learn one set of prefixes, and they work for everything. There's none of this 12 inches, 5,280 feet, 4 cups in a quart, all kinds of crazy stuff like that. Another derived unit is density. The density of a substance is the ratio of its mass to its volume. So we can express this in equation form. Density equals mass divided by volume, or shortened D equals M over capital V. Common units for liquids and solids are grams per milliliter and grams per cubic centimeter. Cubic centimeter is usually used for volumes of solids, and milliliters is usually used for volumes of liquids. But a cubic centimeter and a milliliter are exactly the same size. Density is a physical property. When you measure the density of something, you don't change what the substance is. But it does depend somewhat on temperature, because some things will expand or contract as they get warmer and colder. This is a table of densities that's given in your textbook. The only density that I want you to know is the density of water. This density is true at 4 degrees Celsius. When you heat water up, cool it down, the density changes a little bit. If you were not given other information on a test, then I expect you to assume that the density of water is 1 gram per milliliter. The others would be given to you. There's no point in memorizing densities. We talked about chemical and physical properties on Monday. Now we're going to talk about intensive and extensive. An intensive property does not depend on how much substance you have. And intensive properties can be used to identify a substance. So density is an intensive property. The density of something doesn't change if you cut the object in half. Its mass changes and its volume changes, but the density is the ratio, and so it doesn't change. The melting point doesn't change. Ice melts at 0 degrees Celsius. That's true whether you have 1 ice cube or a bathtub full of frozen water. The amount of substance doesn't change that property. Melting point is another one. The color of an object doesn't change with its size. Those are examples. Extensive properties depend on how much stuff you have. The mass of something. If I have 1 ice cube or 1,500 ice cubes, the mass is different. More ice cubes, more mass, but the density of the ice is the same. If I have a spool of ribbon, might be 9 feet long. If I cut a piece off, the length of the ribbon changes. Its color doesn't change, though. So extensive properties, they're like an external thing. It depends on how much stuff you have. Intensive, I think of intrinsic. It's unique to that substance, and you can't change it just by making more or less of it. Any questions? Mm-hmm.
Is that like qualitative versus quantitative properties?
Is it like qualitative versus quantitative? Not exactly, because both of these could be qualitative or quantitative. So you could have an intensive property that's qualitative. You can have another intensive property that's quantitative. So let's calculate density. This is what I grew up calling a story problem. Now they call these word problems. I have found that there's two kinds of people in the world. People who like story problems and people who hate story problems. There's very few people that are just kind of indifferent. You're in one camp or the other. If you are in that group, which is probably a majority, of people who do not like word problems, I'm here to help you, okay? I can help you figure them out. You can probably do the math just fine. It's the words that mess you up. So if you have trouble with that, keep asking questions and keep asking questions. So this is a problem that's got a lot of words. Most of these words are not important, but we should read them anyway. A man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. He places the ring on a balance and finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? We are given information to calculate the density. Density is an intrinsic property of metals. Different metals have different densities. If you pick up a chunk of aluminum and an equal sized chunk of lead, the aluminum is much lighter. That's why they make airplanes out of it, because it's not as heavy for its size. So what we need to do is figure out what the density is. Well, we can use an equation for that. Density is mass divided by volume. We need a mass, we need a volume. We're going to look through this problem and find the numbers and identify them. Here's a number, and here's a number. Don't drop the units off. The unit is part of the number. So we've got 3.15 grams, and we've got 0.233 cubic centimeters. The question actually says mass of 3.15 grams. If it didn't say that, though, we should be able to look at the unit mass and recognize that that's a mass unit. So this must be the mass of the ring. Then it says it displaces this much water. There was a famous experiment. Now I can't remember the name of the guy who did it. He got into his bathtub full of water all the way to the top. He gets in and a whole bunch of water sloshes over. And he realized something, and he shouted, "Eureka!" He'd figured out that you can displace water and measure volume. If you have a cup that's full to the brim, and you put, maybe you drop your cell phone into it. That would be unfortunate, but it could happen. What's going to happen to the water? Some of it's going to spill out, right? Because the cell phone has a volume, and it's going to displace the water. So the amount of water that comes out is equal to the volume of the object that went in. So this is a volume found by displacement. We can recognize this as a volume by the cubed length units. So this is the volume. So this problem is actually quite straightforward. We identify those numbers and then we put them into the equation. 3.15 grams, 0.233 cubic centimeters. Always include the unit. Every single time you write the number. It's really important. There was a Mars space orbiter that crashed. Millions of dollars lost because two groups of scientists miscommunicated about units. One group was using English units, one group was using metric units. So they calculated the height of the orbit wrong, and the thing crashed. So stupid, right? We're not going to be stupid. We're going to write our units down. Yes, it's a little tedious. Taking the class over again is way more tedious than writing the units. Okay, so I did that. Now I need to do the math. 3.15 divided by 0.233. And my calculator is showing me 13.5193,133. And I need to include the units. Nothing is going to cancel out here. I have grams, I have cubic centimeters, and so I'm just going to copy them down. Grams per cubic centimeter. I haven't told you about sig figs yet, so we're not going to worry about rounding that. There is a decimal point. Any questions? Did that answer the question? No, it didn't. Sometimes we come up with an answer and we're like, yes! Oh, wait. The question is it made of platinum? How do we find the density of platinum? We look it up. Let's go back to this table. See, platinum, 21.4 grams per cubic centimeter. Is that one platinum? Nope. It's mercury. Yeah, that's what the table would tell us. Mercury is 13.55. Mercury is a liquid at room temperature, so the ring's probably not mercury, but it's definitely not platinum. It's probably a mixture of other metals. So the answer is no, not platinum. Any questions? So what does the guy do now that he found out his fiance gave him the wrong ring? Well, he tells her about it. So the woman in this example is shocked that the ring is fake because she wasn't trying to trick him, and she returns it. She buys a new ring that has a mass of 4.53 grams and a volume of 0.212 cubic centimeters. Is the new ring platinum? Well, this is very similar, isn't it? Density equals mass over volume. Here's the mass. How did I do that? Scare myself. Mass is 4.53 grams divided by 0.212. cubic centimeters. 4.53 divided by 0.212. This time it comes out to 21.367, blah, blah, blah. Whole bunch of stuff, grams per cubic centimeter. Is the new one platinum?
Yes.
Yeah. The density of platinum is 21 point something. That's really, really close. Density is an intrinsic property. It can be used to identify things. Any questions? Yes?
For every questions that they don't say it's what is the mass, they just say like 3.15 grams. So we have to know that grams is a measure of mass, not, it's not like straightforward where it says the mass of.
Yes, there will be problems where it doesn't necessarily say the mass is this. It'll just mention, 4.53 grams. And yes, you do need to recognize that gram is a unit of mass.